Good day, everyone. My name is Nnabuike Ngwu from the Department of Mechanical Engineering, University of Nigeria, Nsukka. Today, I will be presenting our study on estimating the potentials for endothermal comfort and electric vehicle charging with really integrated photovoltaic system in Nigeria. So this is the presentation outline. Moving to the background. So Nigeria faces major challenges in cooling demand and energy use. Climate change has caused rising temperatures in sub-Saharan Africa, increasing cooling needs in buildings to maintain comfort. So, as shown in Figure 1A, the distribution of total final energy consumption by sector in 2022 reveals that residential and transport sectors are the main drivers of Nigeria's energy demand. So, on the right, which is Figure B, shows oil consumptions with transport dominating at 91%, primarily from internal combustion engine vehicles, which are the major means of transportation in Nigeria. Additionally, in 2023, about 39% of Nigerian population lack access to electricity, which makes people to rely or depend on diesel generators that makes use of fossil fuels. Also, 77% of generated electricity came from fossil fuels. So this high dependency on fossil fuels drives greenhouse gas emissions and contributes to environmental and economic burdens. So the question now is, how can we break this cycle in a country with unreliable grids and rising heat? So this leads us to sustainable energy options, where solar power emerges as an alternative solution. So solar energy is the obvious choice because Nigeria has a high solar potential, coupled with the fact that PV is the fastest growing renewable energy technology in the world. Meanwhile, electric vehicles are a clean, sustainable alternative to internal combustion electric vehicles, cutting oil dependence. So this brings us to our research question, which is how can renewable energy in particular, building integrated photovoltaic systems simultaneously address energy poverty, cooling demands, and transport electrification? So the research gap, figure 2 shows that BIPV research is advancing globally, but there are a few studies coming from sub-Saharan Africa. So this creates a critical gap that needs to be filled. So with this gap identified, the aim of our study is to evaluate the BIPV energy surplus, electric vehicle charging potential, and associated greenhouse gas emission savings for residential building across various locations in Nigeria. So the diagram here, which is a framework of our study, shows describes that PIP energy generated by PIPV system will be used to maintain thermal comfort, that is, operate HVAC systems and charge electric vehicle. And by doing so, helps to reduce greenhouse gas emissions, which improves the environmental sustainability of the country. So the tools we'll be using in our methodology, tools we used is the Open Studio, which is used to model for modeling the building and simulation of HVAC loads. Then PVGIS was used to calculate the BIPV energy output. We also assessed the electric vehicle charging potential using Tesla Model 3 long range as the case vehicle. Why finally determining the greenhouse gas mitigation. Okay, for the building we selected is a one-story residential building, which is normal in Nigerian homes. So we modeled it in Open Studio using the floor space GIS for precision. Okay, the building's roof is a double pitched roof with a slope angle of 30 degrees. And we also, in Open Studio, we also simulated for the HVAC load, whereby the HVAC system is maintained at the temperature of 25 degrees Celsius and humidity between 30% to 60%. And the HVAC system is only run or operated during occupied periods. That is when the room is being occupied in order to minimize energy consumption. So for the BIPV system, we use the monocrystalline silicon PV system with a conversion efficiency of 23%. So the number of modules integrated in the roof of the building is 64, which covers more than 95% of the available roof area and has a combined peak power of 12.33 kilowatt peak. So we also accounted for the 14% system loss by factoring some inefficiencies such as wiring, shading, dust, etc., which is common in Nigeria. So next, we calculated the energy, electric vehicle, and greenhouse gas emission savings using this equation. So equation 1 was used to calculate the energy generation by the BIPV. Equation 2 was used to calculate the energy generation for a certain number of years while accounting for the relation factor. Then the energy surplus, which is the difference between HVAC load and BIPV energy output and HVAC load, was calculated. So firstly, the energy generated by BIPV was used to operate the HVAC system. Then the remaining, which is the surplus, will be used to charge the electric vehicle. So equation 3 was used to calculate the energy requirements or the energy demand for a specific travel distance of the electric vehicle. While equation 4 used to calculate the number of electric vehicles that can be charged by the energy surplus. So for the greenhouse gas emission savings, so equation 5 was used to calculate the greenhouse gas emission savings from the PV system, which displaces the grid electricity, while also the greenhouse gas emission savings from the electric vehicle that displaces the internal combustion engine vehicles calculated using equation 6. Then we did the electric vehicle charging analysis. So we analyzed the electric vehicle charging potential nationwide and for major cities as shown in figure 5. So here we assume the travel distance that is equal to the full range of the electric vehicle selected. This means that the energy requirement will also be equal to the battery capacity of the vehicle. So we also focused on some states, which is Abuja, Anambra, and Lagos, that represent different climates. So these states are also highly urbanized with good road networks. So using the big maps, we calculated the maximum road distances, which is 195 km for Abuja, 130 km for Anambra, 202 km for Lagos. So using equation 3, we calculated the energy requirement in each state for those maximum road distances. Then the results. So moving to the results, we started with the HVAC load and the BIPV energy generation for the nationalities. So figure 7 shows the HVAC load profile for the urban centers in Nigeria. So in figure 7 shows that the HVAC load are mostly dominated by cooling load. That is, HVAC load are mostly cooling. This is due to Nigerian warm climate. The figure also show that Lokoja has the highest HVAC load, while Jos has the lowest. Then figure 8, which shows the BIPV energy, shows that Damaturu, which is located in the north, has the highest PV energy output due to the highest solar insolation, while Port Harcourt has the least energy output due to lower solar insolation. Then for the case study locations, Anambra exhibited the highest annual HVAC load, while the lowest was recorded in Lagos due to different climatic conditions. We also, from that figure 9, we also noticed that the HVAC load peaked in months in dry seasons, that is March for both Anambra and Lagos and April for Abuja, while HVAC load is lowest rainy seasons. In BIPV energy generation, that is figure 10, the, um, the highest BIPV energy generation was recorded in Abuja, which is which is located in northern part of the country, while Anambra used the least energy due to lower solar insolation. So, also, the figure shows that the highest BIPV energy output were recorded in dry seasons, while the lowest were recorded in rainy seasons or cloudy days, cloudy months. So for the energy surplus, which is different between the PV energy output and the energy and the HVAC load, we noticed for the nationwide that the surplus is highest in Jos. And remember, Jos has the lowest HVAC load or lowest cooling load, while the Port Harcourt records the lowest energy surplus. And but of course, Port Harcourt has the lowest BIPV energy output. So for the case study locations, we noticed that the energy surplus aligns with the optimal solar conditions. That is, it's peaked during the dry seasons, which has a higher solar insolation, and the least were recorded during the rainy seasons. So, for the number of electric vehicles that can be charged, which is shown in figure 13, Anambra has the highest due to the shorter distance. And the shorter distances means that there is a lower energy demand per charge in the states. Also, in all the three locations, at least one full charge per day for maximum distances can be supported in all three locations, except for some modes in Lagos, which are in the rainy seasons and in August in Abuja. So for the greenhouse gas emission avoidance from both the BIPV and electric vehicle charging, which is shown in figure 14 and figure 15, we notice that it increases with latitude. That is, northern areas achieved more greenhouse gas emission avoidance compared to the southern areas due to better solar insolation. So in figure 14 shows that the highest recorded is 22,000 kilogram CO2 emission, while the lowest is 13,000. Then for electric vehicle charging, figure 15, the highest greenhouse gas emission savings were recorded as 48,000 kilogram CO2 emission, while the lowest is 28,000. So for the case study, for the state-based analysis, we noticed that when compared to a study in Canberra, Australia, we noticed that the BIPV system lifetime saving for 20 years is 2 to 3 times more than the one recorded in a study in Canberra, Australia, showcasing Nigeria's strong potential. So the same thing with the electric vehicle charging lifetime savings. Though the one in Canberra, Australia, is for smaller travel distances. So in conclusion, energy surplus from the BIPV represents a resource for sustainable mobility in Nigerian homes, this is described by our study. So our study also shows that there is a strong electric vehicle charging capacity, especially in shorter distance areas, while also showing that there is a significant greenhouse gas avoidance from both the BIPV and electric vehicle operations in the country, which is higher in the north than in the south. So this means that policymakers can incentivize BIPV and integrate it with electric vehicle infrastructure. So this is the end of our presentation. Thanks for listening.